So, we've heard about quantum computers already. In the world of computing, you have classical computers. They work with bits, binary bits. It's an on-off kind of switch. You press the light bulb can be off or on, and these are the computers that we're using every day, smartphones or on laptop, etc. Quantum is bringing a new kind of computer that will work with qubits, and we'll hear more about it later this morning. But the idea is that these qubits have it can encode much more values, and are much more powerful. They will lead to much more powerful computers with certain applications. Great applications to optimize logistics, to do drug discovery, to simulate quantum materials. But at the same time, they will have a negative impact. And this negative impact is that they will impact the cybersecurity that we use. You see on the bottom left, here on this slide, the cryptography that we use every day. You use it every day. You connect to websites, you do e-banking, you don't realize it, but information is protected in terms of confidentiality and authenticity using mathematical techniques called cryptography. There are two kinds of cryptography: public key cryptography and symmetric key cryptography. This is how we do it today. When there will be a quantum computer, the public key cryptography will not work anymore. It won't be secure anymore, and the reason is that it's based on a mathematical problem. The security comes from the fact that this mathematical problem takes a long time to calculate on a classical computer. And this will not be true anymore with a quantum computer. And that's very important because it means that we will have to re-engineer our information security techniques in order to remain secure in a quantum world. What does it impact? It impacts everything. It impacts authentication of software upgrade. When you upgrade your smartphone, the firmware, you want to know that it comes from the right provider and not from an illegitimate provider. Identity management, access and authentication, and confidentiality of data. Everything that we do today online will be impacted. This is what specialists in cybersecurity call Q-Day. The day, so quantum computers exist already, but they're not powerful enough to put to put cryptography at risk. Progress is being made and actually accelerating, and the day when such a sufficiently powerful quantum computer will be available is called Q-Day. We don't know when Q-Day will be, but many governments estimate that we must be ready before the end of the decade. That's only 5 years away. That's a very short time to re-engineer completely the information security infrastructure. What can we do to be secure in this context? Well, we can remain in the math world, keep using mathematics, and just try to find a different mathematical problem, one which is not known to be vulnerable to quantum computing. This is known as post-quantum cryptography and is one approach. The other approach is to rely on physics, to use a quantum principle of physics in order to secure communication. This is known as quantum key distribution, or QKD. And in reality, ladies and gentlemen, I think we actually need to combine both. We need to hybridize both of these techniques in order to have a secure online presence. So, what is quantum key distribution? The idea goes back quite some time. It was invented in 1984 by researchers at IBM and the University of Montreal, and they came up with the first idea of saying, if an imager sends a quantum system, codes information on a quantum system, sends it across on a communication channel, and then a receiver detects this system, then if it's done properly, it's possible to detect interception on this channel. Now, I suspect that not all of you are quantum physicists in this room, and so when I try to explain what I do to my mother, I take a simpler image, and maybe I'll use it today. You can think of communication channels, all communication channels as a tennis game. The imager takes a tennis ball, writes a message on the ball, and then sends the ball across. And the receiver catches the ball, reads the message. And the problem is that someone in the middle could have a butterfly net, catch the ball, and read the message. And that's why you need to secure information when you send it on a network. That is an image of classical communication. Now in the quantum world, it's like replacing tennis ball with a soap bubble. A soap bubble is a fragile object, and if it's intercepted, it bursts, and the emitter and the receiver can detect this interception. Of course, no one uses tennis ball and soap bubbles. In modern communication infrastructure, it relies on optical fibers, and in these optical fibers, there are bright pulses of light that travel through. And these bright pulses of light contain many light particles, many photons, millions. And it's possible for an adversary to take just a little bit of this light to intercept the data. And that's why you need to secure information. Now, in the quantum world, if you send one photon at a time, one quantum particle at a time, then, according to the laws of quantum physics, measurement will create a perturbation, and you can detect this perturbation. This is the fundamental idea behind quantum key distribution. And so from this